Okay, so have you ever watched a massive robotic arm perfectly assemble a car with like millimeter precision? Or maybe you've seen a drone hover completely motionless in heavy winds. And you kind of have to wonder, how do engineers guarantee these machines don't just wildly thrash around, tear themselves apart, or literally drop straight from the sky? Well, hi everyone, and welcome to this explainer. I'm so excited for this one. Today, we are exploring the invisible mathematics that keeps our technological world from spiraling into total chaos. We're diving deep into the brilliant concepts of system stability and a really cool, highly predictive mapping technique called the root locus. To navigate this highly technical subject without feeling totally overwhelmed, we're going to use a map-making metaphor to guide us through 5 clear waypoints today. So first up is the quest for stability, followed by mapping system poles. Then we'll formally introduce the root locus, look at 3 simple rules for sketching it, and finally, we'll see the root locus in real action. All right, waypoint number 1, the quest for stability. Let's figure out these systems. Ultimately, understanding and achieving stability is the absolute holy grail of any control system. But, before we can map anything, we need to know exactly what we're looking for. In engineering, stability has a very specific definition. It means a system produces a bounded output for a bounded input. So, in plain English, if you give a machine a specific limited command, its reaction shouldn't just keep escalating forever. A stable system won't spiral out of control. Instead, its output stays bounded and eventually settles into a predictable, steady state as time moves forward. And this right here brilliantly illustrates that exact contrast. Over on the left, notice the stable systems. Whether they oscillate a bit first or just smoothly taper off, their response naturally dampens and settles down. That is exactly what we want. But look at the right side. With unstable systems, you give them a tiny input, and instead of settling, they grow exponentially. The waves just get bigger and bigger until the whole system breaks or enters total chaos. So the big question is, how do we actually chart out whether our system is sitting safely in that dampening territory or dangerously close to exponential chaos? Moving right along to section 2, mapping system poles. It's time to find our coordinates. So to chart our system, we use specific mathematical coordinates known as poles. Actually, think of poles as the exact GPS coordinates of your system's underlying behavior. We calculate these coordinates directly from the roots of a system's characteristic equation. It's essentially the mathematical DNA hiding in the denominator of its transfer function. These poles pinpoint exactly where our system stands. Now imagine a literal map where we plot these pole coordinates. In the engineering world, this map is called the S-plane. It's split right down the middle by a vertical imaginary axis. And here is the golden rule of our map, right? Keeping our poles on the green left-hand side ensures absolute safety and stability. But if those poles wander across the border to the right-hand side, boom, we instantly enter the red, unstable danger zone. What's just crazy fascinating here is how each precise location strictly dictates physical behavior. Notice how a pole on the far left means a lightning-fast system response. If it lands perfectly on that imaginary axis in the middle, you get sustained, never-ending oscillation. And of course, anything in the right-hand plane, or RHP, is a total disaster, completely unstable. It's really the perfect diagnostic chart. Every single mathematical coordinate beautifully corresponds to a physical reality. Okay, section 3, introducing the root locus and mapping gain. Here is the major conflict that engineers face. Real systems aren't static. So what happens when we increase a system's power, also known as the gain? Enter the root locus. This is a highly predictive graphical map that visually traces the exact journey our closed-loop pole locations will take across the S-plane as we crank up the system's gain, which is represented by the letter K, all the way from 0 to infinity. The absolutely crucial point here is that gain, or K, is the invisible force that actually moves our poles across the map. As the gain increases, the poles literally migrate. This means a perfectly safe system sitting comfortably on the left side of the map can be pushed right across that boundary into the danger zone if we aren't careful about how much power we give it. To prevent engineering disasters, we really need a way to draw this journey before we actually fire up the machine. Which brings us to section 4, 3 rules of sketching. Let's draw the map. I absolutely love this part because we can walk through 3 beautifully simple rules that allow us to sketch this predictive map completely by hand. It totally strips all the intimidation out of the complex math. First up, the real axis test.
We plot points on the real axis if the number of poles and zeros to the right is an odd number. Second, start and end. Every single branch starts at an open loop pole when the gain is 0 and ends at a 0 or travels off into infinity as gain approaches infinity. And third, symmetry. The plot is always a perfect mirror image above and below the real axis. So these rules give us the vital skeleton of our map. They ensure that every single pole has a clearly defined path, and that because complex poles always appear in conjugate pairs, the journey is perfectly symmetrical. Once we hand-sketch this framework to understand our system's fundamental limits, we can then let computer software like MATLAB swoop in to fill in the precise, mathematically perfect curves. All right, final stop, Section 5, Root Locus in Action. Let's look at a practical example.
Let's map out a real scenario. Notice the transfer function here. By just looking at the denominator, we can calculate 3 starting coordinates for our system. We have poles resting precisely at 0, -1, and -2. And notice they are all sitting securely on our safe real axis. Also, in this particular system, we have 0 finite zeros. Next, by placing this system into a standard negative feedback loop and driving it with a variable gain block, k, we're basically going to test its absolute limits. We're setting up a scenario where we can dial up the gain, like turning up a volume knob, just to see exactly how far we can push it before it breaks. Notice the massive contrast we're setting up here. We begin completely safe. At our starting point, where gain is exactly 0, our 3 poles are stationary and calm on the safe side of the map. But as our gain approaches infinity, well, our ending point is drastically different. Because we have no finite zeros to catch them, all 3 paths are destined to aggressively scatter outward into infinite space. And this brilliantly illustrates our final map. This right here is the completed root locus. You can literally watch the journey unfold. The poles 0 and -1 move toward each other, collide, and just break away vertically. Meanwhile, the pole at -2 shoots off endlessly to the left. But look really closely at those vertical branches. Right when the gain hits a specific threshold, when k equals exactly 6, you can see those 2 poles cross the vertical boundaries straight into the dangerous, unstable right side. We've literally just mapped the exact breaking point of this machine. It really leaves us with a provocative thought to wrap up today's explainer. Think about it. If we can completely tame a highly complex, potentially chaotic machine and predict its exact breaking point using just a few simple, symmetrical lines on a graph, what other invisible systems around us in economics, in nature, in society are just waiting for the right cartographer to come along and map them? Thank you so much for joining me today. I really hope this sparked your curiosity to look for the hidden maps all around you. See you next time.